Okay, so this is going to be a lecture over the rest of how to solve a homogeneous linear system. We've talked about already what those systems look like. We've already talked about case one of distinct eigenvalues and eigenvectors, well, distinct eigenvalues, which then produce distinct eigenvectors. We went through that example already. What I'd like to talk about in this video is what happens if we have repeated eigenvalues and what those look like and how we deal with those. So what this means to have repeated eigenvalues is that when you factor the your auxiliary equation, you end up with a repeated root of lambda minus some value, we'll call it lambda 1, to an m power of this characteristic equation, which means that lambda 1 has multiplicity m. In other words, you might have it show up a bunch of times. If you have this happen, you actually can have two different types of solutions. The first type is that you actually can find m linearly independent eigenvectors. And so you would be able to just write your answer as C1 times that eigenvector with e to the lambda 1 on t plus C2 times a different eigenvector times e to the lambda 1t. So even though there's nothing special about this, these are different eigenvectors, so therefore these are different terms. And then you keep doing that all the way up, and you get all these different eigenvectors going even though you have a multiplicity m eigenvalue. So that's one situation you can have, which is different than we had when we did the solutions to just a linear independent with constant coefficient problem. With systems, you can have this happen. The other situation you can have is analogous to what we saw when we had multiplicity of your roots in solving a differential equation, is that you could actually have where you have one eigenvector that corresponds to that. In which case, then you would have, let's say if we have case 2 with multiplicity 2, then you'd have your x1 is k1 times e to the lambda 1t. And then your x2 would be a different eigenvector, k3 times t e to the lambda 1t, plus a different eigenvector, k2 e to the lambda t. So this is a little different than we saw, and we're going to do some examples showing how this works. Usually you let k3 and k1 be the same, and that works out okay. You can't let k2 and k1 be the same because then you wouldn't have linearly independent terms. But if k3 and k1 are the same, you actually can have linear independent terms, and then your k2 depends on your k3 but is different than your k1. If you have m3, so if you have multiplicity 3, things get a little bit more complicated. You'd have an x1, which is k1 e to the lambda t, and that should have a 1 there. And then you'd have an x2, which is k3t e to the lambda 1t plus k2t, or k2 e to the lambda 1t. So kind of what we saw up here with case 2. But now you'd also have another whole set. Notice you had a t to the first power here. Now you'd have a t to the second power if you have multiplicity 3. And then over 2 factorial, the different eigenvector altogether. And then you'd have a different eigenvector, t to the first power over 1 factorial e to the lambda t plus a k4, a totally different eigenvector, e to the lambda 1t. The main thing is of your eigenvectors, k4, k2, k1 cannot be the same because then you wouldn't have linearly independent terms. K5 and K3 could not be the same because then you wouldn't have linearly independent terms. But some of the other ones could be the same. So we're going to do an example of this method of what happens here. So here is an example where we're going to solve a differential equation system of x prime is equal to a times x, where a is your coefficients -1, -2, 1, 0, -2. Notice in this case, a lot of times we don't give the system, this would have been written as negative 2x plus 1y, 0x minus 2y. And so you'd be maybe seeing it this way. We can write them a little differently on occasion. And again, we solve that same equation, same kind of problem that we did before, where you're going to go ahead and solve this auxiliary equation. So we're going to take this determinant of this. So the first thing is to figure out what is A minus lambda I. So let's do that first. Let's write that down because we're going to need that anyway. So we're going to have A minus lambda I. And that would mean, again, lambda is subtracted off the diagonal. So that's what A minus lambda I is. And then we're going to find the determinant of that. So the determinant of A minus lambda I would be equal to negative 2 minus lambda times minus 2 minus lambda minus 0 in this case, because 0 times 1 is 0. And that equals 0. So what we end up having is we end up having minus 2 minus lambda squared equals 0. So lambda is equal to minus negative 2. So we have lambda equal to negative 2, and it has multiplicity 2 because of that square. All right, so what we're going to do is we're going to work with that one and see kind of what kind of eigenvectors we're going to get from this eigenvalue. So we're going to start with lambda equals negative 2. And we'll work with that and see where we go. And again, what we do is we take that and subtract that off the diagonal. So if we go back to our equation here, we have minus 2 minus lambda, 1, 0, minus 2 minus lambda. That's my A. And so A minus lambda I would be minus 2 minus a negative 2, 1, 0, minus 2 minus a negative 2. And so you end up with 0, 1, 0, 0. And that's going to be multiplied by some k. We'll call it k1. And again, that's going to equal 0. Equals the 0 vector in this case. So we'd have basically what you can think of having here is you've got 0, 1, 0, 0 times k1, k2. And so what you end up with when you multiply this together is 0 times k1 plus 1 times k2. So k2 equals 0. And 0 times k1 times 0 times k2. So we end up with k2 equals 0. K1 can be anything. So why don't we make it be 1? Because it's just easier to make it 1. You can't let it be 0 because then we wouldn't have what we need. So you can't let it be 0, but you can let it be 1. So we now happen to have that x1 is the vector 1, 0, my k, which is 1, 0, e to the negative 2t. Remember, my lambda was negative 2. x2, because there's only going to be one of these, because even if you change your k1 to be like 2 and have 2, 0, they're not linearly independent. So I can't actually come up with another k from this that would be linearly independent from this one just by changing that number to 2 or 5 or negative 7. So unfortunately, I will get the second case here where we're going to have a k3 times t e to the negative 2t plus k2 e to the negative 2t. So this is that second case that we were looking at here. So to go back to that for just really fast, we've got this second case here, k3t e to the lambda t plus k2 e to the lambda t. And what we have to do now is figure out what is that k3 and k2. So that's our next step, is to find out what k3 and k2 are so we can actually find out what x2 is equal to. Okay. Now, like I said, we can let K3 be the same as K1. So let's let that happen. Let's let K3 equal 1, 0. There's no reason why it can't do that. Okay. K2 is going to equal a new matrix. And the book likes to use a P for this. So they call this P. And so you're going to have P1, P2. So what we're going to have is, we're basically going to have that K3 is going to equal A minus lambda I, so A minus negative 2I times K2. So that's actually how it all fits into play and where it all comes from. And what we have to do is figure out how to get this to work. So we already know what A minus lambda I is. That was the vector, that was the matrix, sorry, 0, 1, 0, 0. K2 we just called P1, P2 just to give us more letters to work with. And K3 we've defined to be the matrix 0, 1. So now if I did this multiplication, I can see, hey, I'm going to get 1 is equal to 0 times P1 plus P2. And 0 is going to equal 0 times P1 plus 0 times P2. So therefore, P2 equals 1. P1 can be anything we want it to be. So since it can be anything, let it be something nice. I wouldn't let it be 0 because things get kind of weird with 0, but we can make it be 1. So now we have, is we now happen to have that K2 is 1, 1. So it's that's that column matrix. So now that we have that, we can now say that X is equal to C1 times my first X1, which was the eigenvector 1, 0, e to the negative lambda t, negative 2t, sorry, plus C2 times K3, which was the 1, 0 again, t e to the negative 2t, plus this K2 that we just came up with, 1, 1, e to the negative 2t. Again, notice these two terms have the same e's in them, but they're linearly independent because 1, 0 and 1, 1 won't give you the same thing. So that's actually what the answer is to this one. Let's do one more example. So this time I want to solve this problem here. So this is actually a three equations and 3 unknowns problem. So this is a system with 3. Again, it helps to write out what your A matrix is. So my A matrix is the matrix 3, 2, 4, X, Y, Z. X is 2, Y there isn't 1, so it's 0, and Z is 2. And then the last row would be 4, negative 2, 3. So there's my A matrix in this case. All right, so now that I've done that, I can now go ahead and do my A minus lambda I. So we're going to do the exact same thing of A minus lambda I here. Oops. Sorry. A minus lambda I is what I want to do now. So we do the exact same thing we've always done. A minus lambda I, that's the process we do no matter what kind of solutions you have. And again, that means we subtract lambda off the diagonal. So we'd have 3 minus lambda, 2, 4, 2, 0 minus lambda is negative lambda, 2, 4, negative 2, 3 minus lambda. And again, really what we're doing is we're multiplying I, which is the matrix 1, 0, 0, 0, 1, 0, 0, 0, 1 times lambda, and then subtracting that from A. So that's why it's lambda off the diagonal. Okay. So now that we have this, we can now do the exact same thing we did before. Find the determinant of this. You can find this determinant by using your calculator. It's fine to do that. I don't know why I put a 2 there. It should be lambda. So you can use your calculator to do this and find out what that is. So it is, again, go to matrix, go to determinant, then go to matrix and put in a 3 by 3, and then type this in. I wouldn't use lambda because there's no easy lambda on your calculator, but there's other things you can use. So when I did this, I got -1, lambda -8, and lambda +1 squared. Okay. And that equals 0. So lambda equals 8 or -1, but the -1 has multiplicity 2. Okay. So now let's see what happens with this. So we're going to do the lambda equals 8 first because that one isn't multiplicity. So we can do that one first. So again, we're going to look at a minus lambda I times k equals 0. So a minus lambda I means you're going to subtract 8 off the diagonal. So 3 minus 8 is -5. 2, 4. 2. 0 minus 8 is -8. 2. And 4. 2. And again, 3 minus -8 is -5. And then you're going to multiply that by k. We'll call it k1, k2, k3 again. And that equals 0, 0, 0. So when we do that, we get -5k1 plus 2k2 plus 4k3 equals 0. We get 2k1 minus 8k2 plus 2k3 equals 0. And 4k1 plus 2k2 minus 5k3 equals 0. So we have that, and what we have to do is we need to actually solve that and see what happens with it. So I'm actually going to show you how to use your calculator to do this. All right, so we're going to go into our calculator. We're going to show you how to do this. So I need to stop sharing for just a moment so I can change cameras. All right, so now I've got my calculator here. And I want to show you how to make sure you can do this. So you're going to go into your calculator. You're going to go into the menu. And the menu you want to go into is actually the same thing of the matrix menu. We can come down the matrix, hit enter. And what we want to do, because you want to actually find out what K1, K2, K3 is, we're going to use reduced row echelon form. And what that will do is we'll actually take it, do Gaussian reduction to it, and take it from where it is at the moment into a different form. So we're going to hit enter to bring that to the main screen. And it has reduced row echelon form on that main screen. Then we're going to go back in the menu, and we need to put in the matrix. So we're going to create a matrix. We're going to create the matrix, and we need to actually, we're going to have 3 rows. I had such a hard time with that. Okay, 3 rows, but there's actually going to be 4 columns because you actually need that 0 column. So you need all the other values, plus you need that 0 column. So we get the matrix to fill in. So the matrix we're filling in is -5. You can't hit enter, sorry, I always forget that. You have to hit, you have to use the arrows to arrow over. So -5, then 2, then 4, and that equation equals 0. So that's your first equation's coefficients. Your second equation coefficients are going to be 2, -8, 2, and again it equals 0. And then the third one would be 4, 4, 2, -5, and again that one equals 0. Then you hit enter, and it gives you the answer in reduced row echelon form. And the reason we know it's a reduced row echelon form is you have first off one row that's all zeros, which means that we're linearly, we're dependent system because we get a row of all zeros. And then the other rows, they've actually reduced everything down to where you just have one of the seeds, one of the coefficients, and the other ones are all zeroed out. And that doesn't always happen exactly that way, but now we can type this in and see what we get. And actually it didn't happen exactly that way, but the last rows being all zeros is what we wanted. So we're gonna go ahead and write these down. Write down what's in your calculator. All right, so we're gonna go back and we're gonna go back to sharing your screen. And so now I can type out what that gave me. And so what that actually gave me, what it gave me the matrix when I did this, is it gave me 1 times K1 plus 0 times K2 minus 1 times K3 equals 0. And the second row was 0 times K1 plus 1 times K2 minus 1/2 times K3 equals 0. And the last row were all zeros, which tells me again it's a dependent system. And what that does for me is it tells me this row here, I can actually say K1 is equal to K3. And this row here, I can tell you K2 is equal to 1/2 K3. And so what happens in the dependent system is you actually have all the values. We can pick one value and find the other two. So in this case, I can tell you that K3 is, let's say, 2, which means K1 is 2 and K2 is 1. So our K1 in this case is the column matrix 2, 1, 2. So I now know that when lambda equals 8, we end up with x is equal to, x1 is equal to 212 e to the 8t. So we have that one. Now we need to do lambda equals -1. And this one's a little bit more work. We're gonna have to go through similar ideas, but we're gonna have a little bit of an issue here at the end. So we'll see what happens. All right, so again, we're gonna start off with a minus lambda I. I'm gonna multiply that by K2, let's call it. And that's gonna equal 0. So when we do a minus lambda I for this one, we get 4, because -5 minus, or sorry, 3 minus a -1 is 4, 2, 4. The next row would be 2, and then 0 minus a -1 is just 1, 2. And then 4, 2, and again, 3 minus a -1 is 4. And we're going to multiply. Again, I just call them K1, K2, K3. If you don't like that, call them A, B, C, whatever you want to call them. It doesn't really matter. And I get 0, 0, 0. So that gives me 4K1 plus 2K2 plus 4K3 equals 0. It gives me 2K1 plus K2 plus 2K3 also equals 0. And 4K1 plus 2K2 plus 4K3 also equals 0. And again, we're going to use the reduced row echelon form. So you're going to go back into your calculator, do the exact same thing with the reduced row echelon form, and you end up with, this will become 1K1 plus 1/2 K2 plus K3 equals 0. And your other rows are all zeroed out. So you end up with just that, which is not exactly the same as we had on the other one, because now I actually have to pick for 2 variables. So if I went ahead and solved this for, let's say, K1, because K1 is by itself. I mean, I could have done K3 also, but I like to solve for K1. We have that. I can now pick for, let's say, K2. And I could say that K2 is -2 because I don't want to have the fraction. And then I could also pick for K3, and I could say, well, K3, let's pick 1. And then I can solve for K1. So by picking these I picked, we can now solve for K1. So we're going to get -1/2 times -2, which of course is 1. And 1 minus 1 means I get 0 for K1. Which means I actually get K2 is equal to 0, -2, 1. Well, the interesting thing about this is, could I have picked something totally different for K2 and K3? In fact, I could have. I could have instead picked K2 equal to, let's say, again, I don't like having fractions, so I'll pick 2 this time instead of -2. And maybe this time I'm going to pick K3 to be 0. And then what happens is K1 would be -1/2 times 2, which is -1, plus 0 is -1. I mean, I could have picked a totally different values also for these. But what I end up with is this time I find out that my K, and I'm going to give it a subscript just yet, my K is -1, 2, 0. So I want to point out that these two Ks are different Ks. They're linearly independent. They have nothing to do with each other. I can't multiply this one by anything to get this. I could have picked different values for my Ks also, by the way, to get totally different ones. But the whole point is I get 2 linearly independent values. So we can actually call this one K3 because it's different. And now I can actually say, well, my X2 is actually equal to 0, -2, 1 times e to the -t. And I can say that X3 is -1 to 0 e to the -t. So I actually get 3 x's that are linearly independent because these eigenvectors are linearly independent. So I can actually now write my x as being C1 times what we got for 8, which was 2, 1, 2, e to the 8t, plus C2 times 0, -2, 1, e to the -t, plus C3, we got -1, 2, 0, e to the -t. And there's my solution to this system. This is a situation where we get linearly independent, even though we had multiplicity too, we got linearly independent eigenvectors. And that's it for solving this case.